Okay, so this is Chapter 4, Lesson 2, and we are going to focus just on ionic equations tonight. Ionic equations are actually fairly easy if you follow two rules. One, you are systematic and follow the same steps every time. And two, you know your solubility rules. And technically three, because it goes without saying that you should already know your polyatomic ions. All right, so what is a molecular equation? Molecular equation shows the complete chemical equation, or formulas, probably would be a better word. Okay, so if I were to give you an example of this, it would be BaOH2 aqueous plus 2 nitric acid, also aqueous, and that's going to produce 2H2O liquid and BaNO3 aqueous. So there's a couple of things that you should have noticed. It was very seamless when I wrote the products, so you need to know your compounds, how to take words and put them into chemical formulas. Now, your complete ionic equation shows the substances in solution. That are ionized. Now, this is going to build on our last slide of our last lesson. We said that there are three driving forces in a reaction. One in which a precipitate is produced, one in which water is produced, or a weak soluble electrolyte or non-electrolyte, and one in which a gas is formed. So what we mean by that and why that is so important is because a reaction is only considered going to completion when one of those things happens. So let's give an example using our above of these substances in solution. So I'm going to break it apart in front of in ions. So I've got Ba2+, that's the charge on it, that's the ion, aqueous, plus there's 2 OH minus because it says OH2, aqueous, plus 2H plus 2 NO3 minus. These are both aqueous. Then we have the formation of two waters. This is not separated into ions because it formed a liquid. And then we have Ba2+ aqueous and 2 NO3 minus aqueous. So this is referred to as our complete ionic equation, where everything that can possibly be ionized is written as ions. The only things that would not be written is if a liquid forms, such as water, a gas forms, or a precipitate forms. If one of those three things happens, then we leave that substance intact. It is not going to ionize in the water. The net ionic equation shows only what participates in the reaction, not spectators. And I'm going to give you an example of that right now using what we just did. So let's look at both sides of this equation. BA appears on both sides. It's a spectator. OH minus does not appear on both sides. This participated in the reaction. H does not appear on both sides. This participated. NO3 appears on both sides. It's a spectator. And water only appears on the right. So after I cross out my spectators, what's left is my net ionic equation. So 2OH minus aqueous plus 2H plus aqueous yields 2H2O liquid. So that's the difference between molecular, complete ionic, and net ionic. Now you're very familiar with molecular. You've been doing it for a couple of years now, especially if you were in my Regents Chem class. Okay, so to review, to write the complete ionic equation, you're going to start with the balanced molecular equation. So you start with the balanced equation. You're going to break all soluble strong electrolytes, compounds with aqueous into their ions, and then you're going to bring down any compound that has a solid, liquid, or gas as it is. You want to make sure you include the correct formula and charge of each ion, indicate the correct number of each ion, and then write AQ after each ion. Okay, for example, write the molecular equation and complete ionic equation for the metathesis reactions between sodium phosphate and calcium chloride. So, sodium, we know, is Na. It has a +1 charge. Phosphate is PO4 with a -3 charge, so that's Na3PO4. Plus calcium is 2+. Chlorine is -1, so when I drop and cross, I get CaCl2. So the Na is going to hook up with the Cl. That's a +1, -1 ratio. +1, yep. And then the Ca, which is +2, hooks up with the PO4, which is -3, so it becomes Ca3PO42. Now, this is aqueous, this is aqueous, this is aqueous. Calcium phosphate, even though it's not in one of our Nacl-No-Sos, it does form a solid. So we could look in the book for this one. Any of the ones that I give you on an assessment would be part of the solubility rules. Okay, I'm not going to just cross out complete ionic here because it's actually done on the next page. So remember, the net ionic is going to aim to simplify the complete ionic equation and eliminate any spectator ions. To recognize spectator ions, look for ions that are present on both sides of the equation. To convert the complete ionic equation into a net ionic equation, cross out the spectator ions that are present like I showed you and write what's left. I like to cross out the spectators. I like to circle what participated in the reaction and then rewrite it as my net ionic. Okay, so I just rewrote the equation that we just wrote at the top of this screen so it's easier. Now the one thing that we didn't do yet was we didn't balance this equation. So we have to put a 3 in front of the NaCl. Not a 3. Sorry about that. Okay, let's start with our CLs. We have 2 here, 1 here, but we have 3 NAs. So I have a funny feeling that the least common multiple, and we have 2 PO4s over here, so I'm heading down the right path here. Least common multiple here is going to be 6, so this has got to be 2. 2 times 3 is going to be 6 here, and that means 6 CLs, so I have to have a 3 here, and I have a 3 there. So this is going to be a doozy. When I split this apart, I've got 2 times 3 on the NA, so that gives me 6 NA plus 1. I've got 2 PO4, 3 minus. I have 3 CAs with a 2 plus charge, and I've got 3 times 2 on the CLs, so 6 CL with a minus 1 charge. This should be my arrow here. When I open the PowerPoint, it gets rid of the arrows. I don't know why it does it. Then I've got 6 NA here. So that's that. 6 CLs. Then I've got 3 CAs. Oh, sorry, that was my solid. I got carried away. CA3PO42, which is my solid. So remember, to get to my net ionic, I'm going to cross out anything that appears the same on both sides. So I'm going to start with my 6 Na, my 6 CLs, and that's left. So what's left? My PO4 3 minus, my Ca 2 plus, and my solid. So when I rewrite my net ionic, I have 2 PO4 3 minus plus 3 Ca 2 plus, yielding Ca3 PO4 2 solid. These were both aqueous. You have to write the state of matter in the net ionic equations and the complete ionic equations. Otherwise, they're considered incorrect. So if it's easier, just write them underneath. That's kind of what I tend to do so I can focus on the reaction. Okay, look what's going on here. We have ammonium carbonate, which is aqueous. We have aluminum nitrate, which is also aqueous. And then when we do the double replacement reaction, we wind up with ammonium nitrate, which is aqueous, and aluminum carbonate, which is a precipitate. So let's just practice doing a couple equations here. So we've got lead 2 nitrate and sodium sulfate, so that's going to form PbSO4, and this is going to be a solid. Knuckle no so, and lead is one in which it turns into a precipitate. And we also have NaNO3, which is going to be aqueous under 2 rules, the Na rule and the No rule, which are all soluble, no exceptions. We have to balance this one, so we have 2 NO3s, 2 NO3s, 2 NAs, everything else is good. In this last one, we've got copper 2 bromide and sodium hydroxide, so we're going to form copper hydroxide, and most hydroxides form a solid. Copper is not an exception. And then we have NaBr, which is going to be aqueous under the Na rule. Okay, we're almost done. Let's do a couple more. So NaOH plus H2SO4. So what's going to happen here is we're going to form Na2SO4. Under the Na rule, this is aqueous. And we're going to form H2O, which is a liquid. Mg and Cl. What's going to happen here is Mg is going to hook up with the Cl, MgCl2. This is aqueous, and we're going to form H2 gas. Oh, I guess I should see if this wasn't balanced. Sorry about that. Going back to this one up top. So we have two NAs, and we have one SO4, and now we have 4 H's, so we need a 2 here. Now we're balanced. And then the second one, we need a 2 here, and 2 Cl's, and now we're balanced. In this one, we have Zn and CuSO4, so the Zn is going to hook up with the SO4, +2 -2. Sulfates are aqueous, and Zn is not an exception, and Cu solid. So there's a metal being formed. And in the last one, sodium carbonate and nitric acid yields sodium, nitrate, water, and carbon dioxide. Now the reason why I included this here, this is one of those things you have to remember whenever there's a carbonate present. Water and carbon dioxide will form as products. Okay, so this last slide, I know it looks confusing because it says D and E, and we just did that, but these are from a textbook, and I just put these in here because I wanted to stretch that brain again. Separate samples of a solution of an unknown ionic compound are treated with dilute silver nitrate, lead nitrate, and precipitates. Barium chloride. Precipitates form in all 3 cases. Which of the following could be the anion? So let's pair these up. If Br was the anion, then we would have AgBr, and we would have PbBr2, and we would have BaBr2. So what do we know about bromine? Bromine is a cull. It's a part of the halogen, and all halogens are soluble except for when silver, lead, or mercury. So this is going to form a precipitate. This is going to form a precipitate. This will be aqueous. So it can't be that one because it said all 3 cases. Let's move to the nitrates. Well, nitrates isn't going to work because all nitrates are soluble unless what? Unless nothing, because there are no exceptions. Hope you had that one coming. And that means it would have to be CO3. They'd all be solids with CO3, so that was the answer. All right, 3 solutions are mixed together to form a single solution. One contains 0.2 molar lead acetate. The second contains 0.1 molar sodium sulfide, and the third contains 0.1 molar calcium chloride. Write the net ionic equations for the precipitation reactions that occur. What are the spectator ions? This is a pain in the butt question, and it's also a long question. So I'm going to do it as easy as I can, like this. Let's just take our 3 compounds. First of all, I want to point out that CH3 COO minus, which you see here is also written as C2H3O2 minus, which is the acetate ion, which is how I normally write it, but this was from a textbook and it was old school. So I'm going to write it this way because that's what you're used to. So what happens is we've got Pb2 plus and we've got C2H3O2 minus. We have Na plus and we have S2 minus. And we have Ca2 plus and Cl minus. So this is the one that we started with, right? So now we're going to hook Pb up with S and with Cl. So we get PbS and we get PbCl2. Okay? This forms a solid and this forms a solid. Let's look at the next one. Na hooks up with S normally, that's what they gave us, but Na hooks up with an acetate and it hooks up with Cl. So we've got NaCl, which is aqueous, and we have sodium acetate, which is also aqueous under the no rule. Nitrates, right? Acetates and chlorides, all soluble, no exceptions. So this is aqueous as well. And in our last possibility, we've got Ca with acetate, Ca, C2H3O2. That's going to be, under the no rule, it's going to be aqueous. And then we have CaS, which is aqueous. So the only two that formed solids were these two. So the net ionic equation for that would simply be Pb2 plus S2 minus yields PbS solid, and Pb2 plus Cl minus yields PbCl2 solid. Now, obviously, I don't expect you to know every single solubility rule. I wanted you to know the ones that I put on the Knuckle No So cards. There are some other ones. Something like this I wouldn't give you on a test, but you could certainly look up the solubility if you weren't sure about PBS. All right, that's it.